Hello all. Today we will be discussing about RC phase shift oscillator using op-amp. Okay. So we have already learned about the basic principle of sinusoid oscillator, which is the Barkhausen criteria. So this we had dealt with in the last class. That is, you have an amplifier with a gain of A and a feedback frequency selective network beta. So Barkhausen criteria states that for sustained oscillations, the total phase shift around the loop should be 0 or a multiple of 360 degree. Correct. So angle of A beta should be equal to 0, 360 degree or a multiple of 360 degrees. Then the second condition is that the loop gain, the magnitude of the loop gain should be greater than or equal to 1, which means that mod value of A beta should be greater than or equal to 1. So this we had derived in the last class. Now, phase shift oscillator, it consists of an amplifier and a feedback network, correct? As in the block diagram, we know that it will consist of an amplifier and a feedback network. So this feedback network generally consists of R and C elements. That is why it is called a RC phase shift oscillator. The phase shift required is provided by the RC network. So that is why it is called a RC phase shift oscillator. So first let us look into this RC network, a single RC network, and what it does. Okay, so we have an RC network and the voltage is across the resistor R. Clear, the input is marked here and the output is marked here. Okay, so let us look into that a little bit detail. So in S domain, we can draw this RC network as what? So this is the RC network. So in S domain, the resistance will remain the same, R itself, correct? Now capacitor, what is the S domain equivalent of a capacitor? It is 1 by CS. Okay, now input voltage, what will happen to V in of T will become V in of S. V output of T will become V output of S. So output voltage you can write as using the voltage division rule as what? V output of S. V output of S will be equal to R divided by R plus 1 by CS into V in of S. Correct. Using voltage division rule. So this is what we have written here. V output of S is equal to R divided by R plus 1 by CS into V in of S. So V output of S will, I am taking the LCM. So it will be V output of S is equal to RCS by RCS plus 1 into V in of S. So in frequency domain, what will happen? S can be replaced with J omega. Correct. S can be replaced with uh, G omega. So what will happen? The output of J omega will be equal to RC J omega by J RC omega plus 1 into V in of J omega. Clear? I am just replacing S with J omega. Now phase difference between the input and output. So from this equation, I can find the phase difference between the input and output. Correct. So what will be the phase difference between the input and output? So here, phase of the numerator minus phase of the denominator. What is the phase of the numerator? It is 0 plus J. This numerator is what? 0 plus J R C omega. So phase of a complex quantity A plus JB is what? Tan inverse imaginary part by real part. So here it will be tan inverse RC omega by 0. Here it will be tan inverse RC omega by 1. Clear? So the phase will be tan inverse RC omega by 0 minus tan inverse RC omega by 1. So this will become tan inverse infinity. Correct. This quantity will become tan inverse infinity, which is 90 degree. So what will happen? The phi value will be becoming 90 degrees minus tan inverse RC omega. So now we can see that based on the value of this R and C, we can actually get a value of phase, whatever phase we want, correct? Whatever phase shift we want from the between the input and the output, that we can decide by designing the values, properly choosing the values of R and C. Clear? So now the phase difference can be made to 60 degree, correct? Based on the value of R and C, you can make the phase difference to be 60 degree, 45 degree. That is your wish, correct? So now if I have 60 degree, one RC network is producing 60 degree, then two RC network will be producing 120 degree. Correct. So if I want 180 degree, I will be using three RC networks. So on and so forth. Okay. So based on whatever phase shift you want, you can use the multiple number of sections, and you can decide upon what is the phase shift to be provided by a single RC network. Okay. So now let us look into the circuit diagram of an RC phase shift oscillator using op-amp. So as we know, it consists of an amplifier and a feedback network. So this is the circuit of an RC phase shift oscillator using op-amp. So here you can see that this part is the amplifier. So what amplifier is this? This is an inverting amplifier. You can see that the non-inverting terminal is grounded. Okay, so the feedback signal is given to the inverting terminal only. So this part is the amplifier. So I am marking it here. So the one in the blue dotted line box, it is the amplifier, and one which is in the green box is the feedback network. Correct. So this consists of the feedback network. So how many RC networks are there? One, two, three. Okay. So three RC networks are there in the feedback, and the amplifier is an inverting amplifier. So what is the speciality of an inverting amplifier? Inverting amplifier, the phase shift is 180 degree. Correct. The amplifier is an inverting amplifier, so the phase shift contributed by this amplifier will be 180 degree. Correct. So now in feedback network, I am going to use three RC networks, each giving 60 degree phase shift. So what will happen? 60 degree plus 60 degree plus 60 degree. So what is the phase shift provided by the feedback network? It will be 180 degree. Right. So now the total shift will be what? 180 degree that is provided by the amplifier plus 180 degree that is provided by the feedback network, which is 360 degree, which means that the phase condition of the Barkhausen criterion is satisfied actually. Correct. The total phase shift in the loop is 360 degree, which means you will get sustained oscillations. Okay, at a particular frequency that you're going to choose. So this is what is happening in the RC phase shift oscillator. Now we will look into the derivation. What will be the frequency of oscillations produced, and what will be the condition for the oscillations to start. Okay, so feedback network is shown here. Correct. So this is the feedback network. Three RC networks. I have drawn it separately. So this part you have the output is coming from here, and the voltage is fed back to the inverting terminal. Correct. So this is the feedback network. So I'm just going to reverse it so that we know that actually the output voltage is actually the input to the feedback network. Correct. And this feedback voltage is the output of the feedback network. Correct. So I'm just going to draw such that it is ulta. Okay. So that this output voltage comes this side and the feedback voltage comes this side. I'm just drawing it because it becomes easy for me to analyze. Okay, so I have drawn like this. So now let us draw the uh, circuit here again. Now let us do the analysis. So I am going to use mesh analysis. So there are three meshes here. Okay, so this is closed. Okay, so this is output voltage only. So this is a voltage source, correct? Something like a voltage source. So there are three meshes, 1, 2, and 3. I'm marking the mesh currents. So first mesh, I'm marking it as mesh current I1 of t. Second mesh current, I'm marking as I2 of t. Third mesh, I'm marking as I3 of t. Clear. Please note, I am using mesh analysis here. You can use nodal analysis if you want. Okay, so if you have any doubts how to use nodal analysis, you can ask me. I will be putting a video based on that also. So now it would be better if I do the analysis in S domain. So I'm going to draw the S domain equivalent of this particular network. Okay, so first let's draw the network. Please note that in S domain, resistor R remains the same, correct? Whether it is in time domain or S domain, R is R itself. Now, what is the equivalent of a capacitor in S domain? It is 1 by Cs. So each capacitor I am replacing with 1 by Cs. Clear. Now, what is the equivalent of I1 of t? It will become I1 of S. Correct. I'm using capital letters for transform domain and small letters in the time domain. So small letter I1 of t will become capital letter I1 of S. Okay. This I2 of t will become I2 of S, and I3 of t will become I3 of S. Please note these are just variables that are using. Okay, I usually denote what is that Laplace transform equivalents in capital letters and time domain variables in using small letters. Okay, now V output of t will become V output of S, and V f of t will become Vf of S. Okay, so this is the S domain equivalent of the network. So this we will be using for analysis and finding out what is the phase shift that between output this feedback signal and the output signal. Clear. So now let us write the mesh equations. So mesh 1 equation, let us write. So what is that? I will start from here, and then it is a closed path. Okay, so that is what. So minus V output of S plus I1 of S into 1 by Cs plus R into I1 of S minus I2 of S. Clear. So that is the mesh equation. Minus V out. I'm starting from here. So minus V output of S. I'm going in this direction. Plus 1 by Cs into I1 of S. What is the next component? R into I1 of S minus I2 of S equal to 0. We are using Kirchhoff's voltage law. Clear. So now I will group the I1 components together and I2 components together. So what will coefficients together? So I1 coefficients are R and 1 by Cs. So it will become R plus 1 by Cs into I1 of S minus R I2 of S is equal to V output of S. Okay. Now second mesh equation, I'm going to start from here. So it will be what? I'm starting and going in this direction. Okay. So R into I2 of S minus I1 of S plus 1 by Cs into I2 of S plus R into I2 of S minus I3 of S. Correct. So that is the mesh 3 equation. R into I2 of S minus I1 of S plus 1 by Cs into I2 of S plus R into I2 of S minus I3 of S is equal to 0. I'm again grouping the coefficients of each term. So minus R into I1 of S plus 2R plus 1 by Cs into I2 of S minus R I3 of S is equal to 0. Now let's write the mesh 3 equation. So what will be mesh 3 equation? I'm going to start from here and going in this direction. So it will be R into I3 of S minus I2 of S plus 1 by Cs into I3 of S plus R into I3 of S is equal to 0. Okay. Now grouping the coefficients of each terms, you will get minus R I2 of S plus 2R plus 1 by Cs I3 of S is equal to 0. Okay, so now let's write these three mesh equations together. So these are the mesh equations. First mesh equation, second mesh equation, and the third mesh equation. Okay, so first mesh equation is you can see that variables are I1 and I2. Okay, because this mesh it doesn't have a component with the current carrying I3. Correct. Mesh 2 has all the currents because R is carrying I1 and I2. This capacitor is carrying I2. This R is carrying I2 and I3. So it will have all the terms. And this term, third mesh equation, I1 is not there. Correct. So now these three equations can be written in matrix form using because these are three simultaneous equations. You can write this in matrix form. Correct. So what is that? It will be like this. So it is a 3 by 3 matrix. So what is the coefficient of I1? R plus 1 by Cs. What is the coefficient of I2 here? Minus R. What is the coefficient of I3 in this equation? 0. What is the output? V output of it. Clear. And the variables are I1, I2 and I3. That is what is written. In second equation, what is the coefficient of I1? Minus R. Coefficient of I2 is 2R plus 1 by Cs. Coefficient of I3 is minus R. Similarly, the third mesh equation, what is the coefficient of I1? 0. Coefficient of I2 is minus R. Coefficient of I3 is 2R plus 1 by Cs. Clear. So this is written in the matrix form. Now let us, so I'm going to use Cramer's rule. Okay, so why am I finding only I3? What is my, what is my ultimate requirement here? I need to see what is the phase shift between the feedback voltage and the output voltage. Correct. So for that, I need an expression for the feedback voltage, Vf of s. What is Vf of s? Vf of s is the voltage across this resistor. What is the voltage across this resistor? It is R into I3 of s. So I need an expression for I3 of s only. I need not find an expression for I1 and I2. Correct. I need only the expression for I3. So that is why I am going to find only I3. Clear? So let us use Cramer's rule for that. So Cramer's rule, what we will do is, so this is like AX is equal to B. Correct. So Cramer's rule means first we will find the determinant of this matrix. So that is marked using delta. I am going to mark as delta. So delta is the determinant of this matrix. Okay. So I will find that. So what will it be? Expanding. I am going to expand using this row. So it will be R plus 1 by Cs into 2R plus 1 by Cs into 2R plus 1 by Cs, which is 2R plus 1 by Cs whole square, minus R into R, which is R square. Now plus R, because it is minus of minus R, plus, so plus R into minus R into 2R plus 1 by Cs minus 0 into minus R. So you will be getting like this. Okay, now I am expanding this 2R plus 1 by Cs the whole square, which will be 4R square plus 4R by Cs plus 1 by C square S square. That is what is written here. And I am expanding this minus, I am taking out, and this R into 2R will be 2R square. This R into 1 by Cs will be R by Cs. Clear? Now 4R square minus R square will be 3R square. Okay, so 3R square plus 4R by Cs plus 1 by Cs square. This also I am multiplying, so it will be R into 2R square 2R cube, R into R by Cs, R square by Cs. Clear? Now I am going to multiply this, so you will be getting like this. Okay, I'm just multiplying, and then finally I will be getting the delta value as R cube plus 6R square by Cs plus 5R by C square S square plus 1 by C cube S cube. Okay, now I will find, second step is I will find the delta 3. Okay, so delta 3 means what? Delta 3 is the determinant of A matrix such that the third column is replaced with the output matrix. So delta 3 will be this matrix where the last column, the third column, is replaced with this. Clear? So now again I am expanding using the first, I'm going to expand using this column because these two are 0, so it is easy. So what will it be? V output of S into R square minus 0. Correct. Minus 0 into something plus 0 into something. So it will be what? Only delta 3 equal to V output of S into R square. Clear? So this is delta 3. So what is, so delta I'm writing it here for again for reference, and delta 3 also I'm writing. Okay. Now what will be I3? I3 will be, according to Cramer's rule, I3 will be delta 3 by delta. Correct. What will be I2? Delta 2 by delta. What is I1? Delta 1 by delta. But we don't want I1 and I2, so I am finding only I3. Okay. So I3 of S will be equal to delta 3 by delta. I'm substituting the value. So V output of S into R square by R cube plus 6R square by CS plus 5R by C square S square plus 1 by C cube S cube. Okay. So in the denominator, we can take the LCM. You will get R V output of S into R square C cube S cube by R cube C cube S cube plus 6R square C square S square plus 5 RCS plus 1. Okay, I'm just taking the LCM of the denominator. Okay, so that C cube S cube will come here. That is what is happening. Okay, so that I'm writing here again. I3 of S is this. Now, what is a feedback voltage? Then what will it be? V of F of S will be equal to R into I3 of S. Correct. So I'm substituting I3 here. So what will happen? R into V output of S into R square C cube S cube by R cube C cube S cube plus 6 R square C square S square plus 5 RCS plus 1. So this R and R square you can multiply, so it will become R cube. Correct. So it will be like this: V output of S into R cube C cube S cube by R cube C cube S cube plus 6 R square C square S square plus 5 RCS plus 1. Now, what will be the feedback factor then? Beta. Beta is always what? Vf of S by V output of S. How much voltage is fed back to the input? How much part of the output voltage is fed back to the input? That is what is called feedback factor. Correct. So Vf is the feedback voltage and V output is the output voltage. So beta will be what? Vf of S by V output of S. So beta is Vf of S by V output of S. It will be, so this V output I am taking this side, so you will get R cube C cube S cube by R cube C cube S cube plus 6 R square C square S square plus 5 RCS plus 1. Okay, so that I'm writing it here again. So I want to find the frequency domain equivalent. So I will replace S with j omega. So what will happen? Beta will become R cube C cube j omega cube by R cube C cube j omega cube plus 6 R square C square j omega square plus 5 RC j omega plus 1. Okay, so frequency from Laplace domain, frequency domain, if you want, you just replace S with j omega, where omega is the angular frequency. Correct. So now j omega cube means what? J into j into j. J into j is minus 1. So j cube will be minus j. So this I am writing here: minus j r cube c cube omega cube minus j r cube c cube omega cube. J square will be minus 1. Correct. My j into j is minus 1. So minus 6 r square c square omega square plus j 5 rc omega plus 1. Okay. So I'm just multiplying it by j numerator and denominator so that it will become an expression which is easy. That's all. Okay. So it will become j into minus j r cube c cube omega cube j into. Okay, so this real part and imaginary part I have grouped together. So in here, real part is 1 minus 6 r square omega c square omega square. Okay, and imaginary part is j into 5 rc omega minus r cube c cube omega cube. So I am multiplying those two. Okay, so multiplying numerator and denominator by j. What is j into minus j? J into minus j is plus 1. Okay, and j into j is minus 1. Okay, so this I can write like this. I'm writing the real part here and the imaginary part here. Okay. Okay. Negative, I am making positive so that it will become r cube c cube omega cube minus 5 rc omega. So this is the feedback factor. Correct. So the phase of this feedback factor will be what? Let us denote it as phi. Okay. So phi is equal to angle beta. So phi will be equal to minus tan inverse. So numerator phase is 0, correct? Because there is no complex quantity here. So it will be minus tan inverse imaginary part by real part, correct? So 1 minus 6 r square c square omega square by r cube c cube omega cube minus 5 rc omega, correct? So according to our requirement, what should be the phase of the feedback network? The amplifier is giving a phase of 180-degree because it is an inverting amplifier. So the phase provided by the feedback network should be what? 180-degree, which we have already told, correct? Each providing 60-degree, so 180-degree it should provide. So phase of the feedback network should be 180-degree in this RC phase shift oscillator, correct? So this will happen when what? This phase is equal to 180-degree, correct? So 180-degree is equal to minus tan inverse this thing. Okay, so I'm writing it like this. I'm taking tan on both sides, so it will be tan 180 is equal to tan of tan inverse, which will be 1 minus 6. Okay, like this I can write. Now what is tan 180? Tan 180 is 0, Correct. So 1 minus 6 r square c square omega square by r cube c cube omega cube minus 5 rc omega should be equal to 0. What does that mean? It means that 1 minus 6 r square c square omega square should be equal to 0. It means that omega square should be equal to 1 by 6 r square c square. It means that omega should be equal to what? Taking square root, you will get 1 by square root of 6 into rc. But what is omega? Omega is 2 pi f, which means 2 pi f should be equal to 1 by root 6 rc. So what is f? F is 1 by 2 pi root 6 rc. So the frequency of the sustained oscillations produced in this particular RC phase shift oscillator will be 1 by 2 pi root 6 into RC. Clear? So we have now derived the expression for the frequency of sustained oscillations. Okay, now we have shown this omega equal to 1 by square root of 6 into RC. We had shown the feedback factor as what we, that also I am writing here. So at this particular value of omega, what will be beta? Beta will be, I will just substitute this value of omega. So r cube c cube, like this it will come. Okay, everywhere I am substituting. Omega equal to 1 by root 6 RC. So this I'm writing here again. Okay, so this after expansion it will be like this. Square root of 6 cube will be 6 square root of 6 r cube c cube, r cube and c cube, r cube c cube and r cube c cube will get cancelled. R cube c cube, r cube c cube will get cancelled. RC and RC will get cancelled. This is 1 minus 1, that is 0. So that the imaginary part will become 0. Okay, so it will become like this. So you will get beta as minus 1 by 29. Okay, so beta is minus 1 by 29. So the loop gain, what is the loop gain? A into beta, correct. So A beta will be equal to minus A by 29, correct, where A is the gain of the amplifier. For sustained oscillations, what is that? Magnitude of this A beta should be greater than or equal to 1. So what is that? Minus A by 29, mod of minus A by 29 should be greater than 1. What does that mean? Mod of A should be greater than 29. It means that the gain of the amplifier should be greater than or equal to 29. For sustained oscillation, the gain of the amplifier has to be greater than or equal to 29. Now, what is the gain of this amplifier? R minus RF by R1. Correct. So mod of minus RF by RF by R1 should be greater than 29, or RF should be greater than 29 times of R1. Clear. So that is so we will summarize it here. The frequency of oscillations produced will be what? 1 by 2 pi root 6 RC, and the condition for sustained oscillations is A should be mod of A should be greater than 29. The gain of the amplifier should be greater than 29, or RF should be greater than 29 times R1. Clear. No, this circuit will also work, but a practically circuit I'm going to write here. So these this resistor and this resistor, it is actually according to virtual ground, this R1 will be grounded, correct, because plus is grounded, correct. So these two are effectively in parallel. So these I am going to replace using a single resistor R. Okay, clear. So this is the practical circuit that which I will be simulating. The other circuit also you can simulate. Okay, it will work. So this is the circuit, and the formula sheet is frequency of oscillations produced is 1 by 2 pi root 6 RC. Condition for sustained oscillations is mod A should be greater than 29, or RF should be greater than 29 times R, because here R is the, here gain is RF by R. Clear. So let us do a small tutorial. Design an RC phase shift oscillator for a frequency of 1 kilohertz. So F is 1 kilohertz, that is 1 into 10 power 3. So frequency of oscillations is given by F is equal to 1 by 2 pi root 6 RC. Correct. So 1 by 2 pi root 6 RC should be equal to 1 into 10 power 3. Okay, so let us take C as 0.1 mu f. So what will be R? R I can substitute for the value of C here, and you can find the value of R. So it will be 649.747 ohm. I'm taking it as 650 ohm. Now RF should be greater than 29 times R. So what is RF? RF should be greater than 29 times 650, which is RF should be greater than or equal to 18,850 ohm. So which is 18 kilo ohm. So I will be using a 15 kilo ohm resistor in series with the 10 kilo ohm potentiometer, so that I can vary, so that I will get the oscillations at one particular frequency. Okay, so this is the sorry, this is the circuit diagram. Okay, so circuit diagram will be like this. Clear? I'm plugging in the values. Okay, now we'll just see this simulation also. I am using multi-sim live. Okay, so the circuit I have drawn here. Okay, so this is the circuit. Okay, this is the circuit. 650 ohm, 650 ohm, point 0.1, point 0.1, point 0.1, 650, 15 kilo ohm and a 10 kilo ohm pot in series. Okay, now I will run this. Okay, I'll split so that I can see the waveform and the graph together. So you can see that there is nothing coming, correct? So now I will slowly increase the potentiometer. Okay, so 5% I'm increasing. Okay, I'm slowly increasing 11, 12%, 14%, 15%. At one, please be careful. You can see it will slowly start. This oscillations will be starting. Can you see that? Oscillations has started, and you can see that it is not a sign here. So I will slowly reduce the gain so that a particular will get a very good sine wave. Can you see that? Now it is a sine wave. Okay, so I'll just show the graph itself so that it is. I will use single so that it will be. Hmm? You see this? Okay, so uh, this is 5.02 seconds, and this is 5.026 seconds. So almost here you can see. Okay, if you want, you can vary the time period also. I mean times per division so that the waveform will look. Okay, I hope this is clear. Okay. Hmm? So if I change this to none, it will show. Now if I reduce this RF, slowly you can see that it is getting gone. Oscillations will die off because the gain has reduced. Clear? If I increase the slowly it will start. So understood. Okay, so this was a tutorial and also and simulation also I have shown. So if you have any doubts, do please ask. Thank you for your kind attention. Have a great day.